We're going to be taking notes on two theorems today. The one that you guys were just looking at in the Desmos activity was about IVT. IVT is more important, so I'm going to spend more time on it. Squeeze theorem is less important, so I'm just going to do it first and get it out of the way. Because it's a not as much of a big deal. But every now and then you might see a question about it. Here and there. You don't have to write that part in the parentheses if you don't want to, but you can. All right, so let me write this definition and then we'll talk about what it means. Okay, so what squeeze theorem says is that if f of x is less than or equal to g of x, which is less than or equal to h of x, for all values of x on some interval that we're given, and the number a is part of that interval, and the limits for h and f, so that's the small one and the big one, both exist at x equals a, and it's the same number. So visually what that would look like is we have A, we have L, so L is some y coordinate, and we have our function, let's just put a little point right there. We have our function f of x, which is like the small function, so it's there. And then we have h of x, which is the big function, so it's there. I always had a hard time with math theorems, just like understanding what they actually meant. Like I read a sentence like that and I'm just like, what does that mean? I don't understand it. So I like to draw pictures to accompany them, and I like to talk about them in pieces. So far we've just talked about the if. If all these things are true, then what? Turn to your neighbor. What can we say is true? It's going to be about g of x. That's going to be our conclusion. Talk to your neighbor. G of x also equals a. Or what color should I use? I'll just use black. Okay, so we know g of x has to be between these two functions. It has to be less than or equal to h or greater than or equal to f. So it's going to be here. What did you guys say as your conclusion? As your possible conclusion? Yes. Yes. So what we'll write is then the limit of, not f of x, I started to write f of x, the limit of g of x as x approaches a equals L. It's basically being squeezed. All right, G can look however, but it has to be squeezed between those two things because of our requirements or our initial condition there. That's what I'm trying to say. So there's g of x. I should have labeled these. I just color coded. So we won't do an example of that right now, but we will see one of these days. Hopefully this is making sense. It's like the function has to be between those two. The big one and the small one meet at the same point. The middle one also has to go through that point. So we'll look at an example a little bit down the road, but I want to make sure we have some good time for IVT today. So that's squeeze theorem. Intermediate value theorem. This is a big deal. This one's really important. We often abbreviate this one IVT. Again, you guys that were in AP Pre-Calc last year, you saw this. There's a few things that are in AP Pre-Calc that are not in regular Pre-Calc, but we still do in calculus. For example, derivatives, all the derivative rules. If you were in AP Pre-Calc last year, you learned those. Anything that you didn't learn in regular Pre-Calc that we're going to cover in calculus, I'm going to teach as though it's brand new. So if you came from AP Pre-Calc, don't just assume, oh, I know IVT, I know I can do this. Go ahead and lean in, and this is your chance to really master it. Same thing when we get to derivatives. We haven't done derivatives yet. We will, but the folks from regular Pre-Calc haven't even seen derivatives yet. So that I'll teach that as though it's brand new as well. So it's your chance, if you're coming from AP Pre-Calc, to really master everything this time around. And if you're here from regular, welcome, enjoy. It's gonna be great. So anyways, let me write out IVT, but basically you guys just did a little exploration. The key with IVT, actually let me explain the basics of it first, like the not real definition, informal definition, let's call it. Don't use this when you answer questions. Don't use this as your justification. So if f of x is continuous and has two endpoints, IVT basically guarantees that it's going to hit every y coordinate in between the two endpoints. And so the key, which hopefully you saw in the Desmos activity, is that the function does have to be continuous. Like if there's some break in the graph, you might have thought the graph was going through a 0, but actually it was not continuous, and so it doesn't have to. But if the function is continuous, we're guaranteed to hit every one of these y values right here along the way. Now, we could hit more than that. The function could look like this. But we don't know. We're just guaranteeing the ones between the two endpoints. That's the key of IVT. So let's write the formal definition. Give me a lot of letters in this one. Sorry in advance. So just to reiterate it, say that g of x is continuous, find the y values of the endpoints, plugging in -1 and 1. Say that 5 is between those two y values, and then kind of repeat this sentence here that I wrote. Except you're going to say it such that g of c equals 5.
You have to say by the IVT.
No, you do not have to say by IVT. In fact, don't. It's not wrong if you do, but if you call it MVT by accident, then that would be wrong. We do have an MVT, which we'll learn later. So you actually do not need to name the theorem that you're using. Thank you for asking it. That's what's different from last year. Okay, here's what we should get. Some options here. You don't need to show this work of actually plugging it in. You could just say what the value is. You can also show the work, that's fine. Right here, I could also say 5 root 2, and here I could say negative 5 root 2. I prefer to use these, but that's my personal preference. And then there's our answer. There must exist a C on the interval. You can use brackets or parentheses, it doesn't matter. Such that g of c equals 5.
Could we also say less than or equal to? And
Yes. You could do it like that. There must exist a C such that it's greater than -1 and less than 1. Yes. You could say that as well. Yep. Again, don't need to say by IVT. I recommend you don't say it, just in case you get confused with another theorem later on in the year. We've established all the conditions for IVT. We have our conclusion, so that's all we need. Okay. I want you guys to do examples 5, 6, and 7 on the next page. I want you guys to do numbers 6 and 7 on the next page.
Three is obviously that then G, if it's just defined for all of it, like same thing here, we probably do like all sorts of if it's just defined.
And then there's always values. And it's
But it's increasing, then it can't like just do this, right? It has to be constant.
Okay, let's talk about these. For number 6, hopefully you circled number 3. 3 is definitely true. G has to be continuous on an interval. Could we circle either of the other ones? Is it enough for G to just be defined? No, because we need it to be continuous. It might be defined but not continuous. Increasing, does that have anything to do with IVT? Could it be increasing and not continuous? Yes, it could. Okay, so that's not helpful. What'd you guys choose for 7? B. B is correct. So here, C is between these two x values. We need the x value to be between the two x values. And 1 is the y value that's between -1 and 7. So D is probably the most common wrong answer. But there you go.